This is what happens when we supply too much voltage to our electronic components. The components will burn out and even explode. To stop this, we need one of these, a voltage regulator. And I'm going to show you how it works, how to design one, and even turn it into a fully working, professional-looking printed circuit board to use as a power supply and even charge a phone with it. You can even download a copy of my circuit board too, links in the video description down below for that. The purpose of a voltage regulator is to keep a constant output voltage even when the input voltage changes. Why is that important? Because the electronic components are only rated to handle a certain voltage. Take this LED for example. If we connect it to a 9-volt battery, it will instantly be destroyed forever. That's because of this thin wire inside the LED. Looking under a microscope, we can see the voltage pushed too many electrons through the wire, which caused it to burn out. To protect the LED, we need a resistor. This will reduce the current. This is only a 10 ohm resistor, which is connected to my variable DC power supply. When we apply a small voltage, we see the LED is fine. But as we increase this, the resistor bursts into flames and the LED will be destroyed. So, using a resistor works well, but the voltage must remain fairly constant. We therefore need a way to ensure a constant output voltage even when the input voltage is varied. Let's say we want to maintain a constant 5-volt DC supply and enough current to charge a simple cheap phone. We want to be able to connect this to multiple voltage sources such as 9 volts or maybe 12-volt batteries. To achieve that, we need to use an integrated circuit component. There are lots to choose from, which can all work in different voltages, but from a bit of research, I found this one, the LM7805. This can maintain a constant 5-volt DC output and up to 1.5 amps of current. This component can be connected to any DC supply voltage between 7 and 35 volts, so it's perfect for our needs. It has 3 pins. Pin 1 is the input for unregulated voltage, pin 2 is the ground pin, and pin 3 is the regulated 5-volt output. The manufacturer recommends a capacitor on the input and the output. It notes that the input capacitor is required if the regulator is far away from the power supply filter. We are going to be using some long wires to connect the battery, so we will use the recommended 0.22 microfarad capacitor. This is an electrolytic type capacitor. We can use a slightly larger capacity version, but we don't want to use a smaller one. The capacitor is going to help smooth out interruptions to the supply and also low-frequency distortions. In this simple example, you can see the LED turns off instantly when the power is interrupted. But if I place a capacitor in parallel with the LED will remain on because now the capacitor is discharging and powering the LED. So the LED is almost unaffected by the interruptions. We're going to add another capacitor in parallel on the input side. This is a bypass capacitor. This is placed very close to the regulator input pin. This will be a small ceramic capacitor, which is typically 0.1 microfarads. The purpose of this capacitor is to filter out the noise and high-frequency distortions from the power supply, as we might not always get a perfectly flat DC supply. We will also add another 0.1 microfarad bypass capacitor on the output side, as well as a 10 microfarad electrolytic capacitor. This is just a typical value used for this purpose. We could use a slightly higher capacity version if we wanted to, but this will work fine. These are going to help ensure we have a clean output on our connected circuit. We will also add a protection diode on the input side. This will help protect the circuit if we connect the power supply the wrong way. To show how it works, if I connect this incandescent lamp to a power supply, it will illuminate. I can reverse the leads and it will also illuminate. If I place a diode on the red wire and connect this to the positive, it will again illuminate. But now, when I reverse the leads, the diode blocks the current and the lamp remains off. So we can use this to protect the circuit. We can use a rectifier diode or a Schottky diode. Here you can see I have placed two LEDs, each connected to a different type of diode. As I slowly increase the voltage, we see the LED connected to the rectifier diode is not as bright. That's because this type of diode has a large voltage drop. If I measure across the Schottky diode, we have a voltage drop of around 0.3 volts, and the rectifier has around 0.66 volts, so it's better to use a Schottky diode for this application. Now we can lay all these components out on a breadboard to test it out, like I've done here. And once we're happy that it works, we can now turn this into a printed circuit board. We're going to be using Altium Designer for this tutorial as they have kindly sponsored this video. All our viewers can get a free trial of this software using the link in the video description down below. So open Altium Designer and click File, New Project, then give the project a name. Right-click the project and add a schematic, then right-click again and add PCB. Now right-click the schematic and save this. Give it the same name as the project. Then also right-click the PCB and save that too with the same name. Now we need to add the components. We can use the Components tool on the right-hand side, but I'm going to use an add-on which will make this a little bit easier. So we find the parts we require. I'm using Mouser, but you can use whoever you wish. I found a 22 microfarad capacitor, so I take this part number and insert this into the library loader and click Search. It then finds the component, so I click Add to Design. It will place the component in the lower corner, so I just need to move it into position. Then we rename the component just to make it easier for us. Now we do the same for the other input capacitor, copy the part number and search for it, then add it, move it and rename it. Then we find the regulator and we add this to our design. And then we find the protection diode and we add this to our design. By the way, I'm using this one, but I would recommend you choose one with a higher current limit. And then we find the output capacitor. We add this and then we rename it. We now need to find the connection terminals and we add this too. We need another capacitor on the outlet, so we select the existing one and copy and paste that and then move that into position. And we do the same for the connector type on the input side. Now we just rotate the components, so select the input connector and press the spacebar to rotate it. Then we rotate the diode, then we can rotate the capacitors, but do make sure that the plus symbol always goes to the positive power supply. The other ceramic capacitors do not have a polarity, so these ones can face either way, but we'll keep it in this order. Then we rotate the regulator and we'll also move the text. Then we rotate the next capacitor and the other capacitor, and now we just move the components into position. Now click the wire tool and start to connect the components together, bringing the ground wire around to the regulator. Then we add a ground symbol to this wire. Now use the wire tool to connect the output side as well. Now add the annotation for the input supply, which is VCC. Then add the annotation for 5 volts on the output side and rename this. We can also add some text for the output voltage and also the input voltage too. Now we need to number the components, so click Tools, Annotation, Annotate Schematic. Then select Down then Across, and then update the change list, click OK, accept the changes, then validate the changes. Then execute the changes and close. Now we see the components are all numbered. Next we need to validate the design. So click Project and then Validate Project. If we click View, Panels and then Messages, it tells us the compilation was a success with no errors. So now click on the PCB and click Design, and then Import Changes. Then validate the changes and then click Execute Changes. The components are placed in the lower corner. Just click the box and delete it. Looking at our schematic, we have the connector J1 on the input, so we'll move that. Then we have the diode and capacitor 1 and capacitor 2, so we'll move these into position also. Then we have the regulator, then we have capacitor 3 and 4, and then we have the output connector. We now rotate the components to make the route for electricity to flow. We can switch to 3D mode to check how it looks. Then we can align the components to improve the appearance. Now click down here, and in the new window, select Mechanical Layer. Right-click and create New Layer, and name it Cutout. Change the settings and then close. Now select your layer down the bottom, then click Edit, Origin, and Set. Then click the top corner of the circuit board. Now click Place and choose Line. Draw a line around the components. Then, while holding Shift, click on the 4 lines. Then click Design, Board Shape, and Define Shape. We can then also see it in 3D. Now I'll just change the text size so it doesn't print too big. Now click on Top Layer and then insert some text, and we'll name this 5 volts, and we can just rotate that. We'll also do the same for the ground text. Looking at the input side of the board, I've just realized the input connector is the wrong way around. We can see that in the 3D view. I just missed it earlier, so I'll just correct that now. Then we add the ground and the VCC text to the board. Now click Root, Auto Root, and select All. It then adds our root to the board. We can also move the root if we want to. Now we go to Tools and Rule Checker. Click Run. It loads a report and tells us that we have 2 problems on the silk and solder mask clearance. We go Design, Rules, Silk to Mask, then change the value, click Apply, OK, then run the rule checker again. Now we see there are no errors. We can see the root in the 3D design now also. So let's save that. Click on your schematic and then click File, Smart PDF. Then choose the schematic. I'm turning off the bill of materials, but you can leave this on if you want to. Click Finish and it generates a PDF of our design. Close that, then click on the fabrication output, choose Gerber files, and then choose the project. Now click that and change it to millimeters. Then on layers, you can leave this as it is, but I'm going to select all the layers and click OK. Click on Folder Structure and then link the file and click Generate, and that's it, we're done. We are ready to have our circuit board printed. Now we need to order our PCB. I'm using JLC PCB, who have also kindly sponsored this video. They offer exceptional value with 5 circuit boards for just $2. I'll leave a link in the video description down below for that, do check it out. I'm just changing the shipping destination and currency to the UK, as that's where I'm based, but you can choose your own country and currency. Now I simply upload my Gerber files and it will produce a preview. We have a number of options to customize the product. I'll choose the quantity and then I'll leave the rest as default. Then I'll save this to cart and go straight to the checkout. We can choose the postage option to decrease the cost, but I want this very quickly, so I'm going to order through DHL Express. Then we just submit our order and pay, and that's it. Simple, done. A few days later, our circuit board arrives in the post from JLC PCB, ready for us to build. I must say, it looks pretty amazing. I'm very happy with this service. Don't forget, you can also download a copy of my circuit board for free. Links for this in the video description down below. Building the PCB is pretty easy. We simply lay out our components, and I like to place them in order on this soldering mat. I'm also using a holder just to make it a bit easier to work with. Then we insert the components and we start to solder them one at a time. Just bend the legs slightly to hold them in place. As you solder the components in place, just inspect the solder joints to make sure it's okay, and then you can trim the leads. And then, after a few minutes, we will end up with our completed circuit board, which is ready for testing. To test the circuit board, I've connected a 9-volt battery to the supply, and the multimeter reads 5 volts on the outlet. If I reverse the battery, we see 0 volts on the multimeter, so the diode is protecting our circuit. I'm happy with this, so I place a small load on it, and it works great. Now, for the real test, I connect a USB port on the outlet, and I plug in a cheap phone. We can see the 9-volt battery is now charging the device. Using a USB tester, we can see it is supplying 4.6 volts and drawing a current of 0.26 amps, so it is working perfectly. Okay, that's it for this video, but to continue learning about electrical and electronics engineering, then check out one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn, and of course, theengineeringmindset.com.